All right, so now we're going to look at part 4. It's basically just an example, and I'm going to do one more example in a part 5. But this is an example of using the central limit theorem and what we learned in section 8.1. All right, so here we're going to look at an example. This came from one of the homework questions. Don't think it was one that I actually selected for you all to do, at least not in the 8.1 homework, but it's similar to those that are in the homework. This one says that suppose a geyser has a mean time between eruptions of 84 minutes. So this could be something like Old Faithful in Yellowstone National Park, where they know about how long it's going to be for the next geyser to erupt. So suppose that there is a geyser. We're not going to name which one this is. This is just a random one. Let the interval of time between interruptions be normally distributed. So we already know it's normally distributed with a standard deviation of 27 minutes. All right, so basically what we have now known to us is that there's a population mean of 84 minutes and a population standard deviation of 27 minutes. So back in chapter 7, we learned how to answer a question like part A. What is the probability that a randomly selected time interval between eruptions is longer than 97 minutes? So what this looks like, I'm going to go to a blank screen so we can draw this out and do what we would have done in chapter 7, which is what we did before spring break. And we'll work this one out. All right, so basically this is like having a sample of size 1. We don't really call it that. This is just a normal distribution. We know it's normally distributed. So I can draw my normal curve. And I'm told that my mean is 84. And that my standard deviation is 27. Now again, this is back to chapter 7. Not chapter 8. Chapter 8 is when we're taking samples, but there's a difference, and we're going to look at how they're worded so we can see what the difference is. And then we're specifically wanting to know what are the chances, or what's the probability that we had a wait time, an individual, so just X, a wait time of more than 97 minutes. So that's where this X greater than 97. So I'm going to mark 97 over here. And then I'm going to shade more than 97, means I'm going to shade to the right. Okay? Now, I'm going to want to put this in my calculator. And luckily, I have a lovely calculator emulator on my computer. And I was able to get this picture, I'll pull it in, of my calculator. So here's what the calculator looks like for this problem. We're going to do normal CDF. And again, this is just what we did in chapter 8 when we did our normal distribution, trying to find the area under the curve. Area is probability. And so I've set my lower to be 97, my upper to be 9999. Of course, you can also use the small caps E99. Either one's fine. You just need a really big number. My mean is 84 and my standard deviation is 27. So when I calculate that, let's see, I end up getting, this area is 0.3151 if I round to 4 decimal places. So there's about a 31 to 32% chance that I'm going to have to wait more than 97 minutes between interruptions. So, or eruptions, sorry. Between eruptions. So that's, you know, that's possible. If there's a 30% chance of rain, I'm probably going to at least make sure I'm not wearing flip-flops and that I have an umbrella in my car. So, you know, that's enough of a chance of rain that I don't want to get caught having to walk around in it. So that's, again, that's just remembering how we did things back in chapter 7. All right, this next part, so same setup. We still have geyser where the mean time between eruptions is 84 minutes. Standard deviation is 27 minutes. We expect it to be approximately normal or normally distributed. So now we know what is the probability that a random sample of 10 time intervals between interruptions has a mean weight of more than or longer than 97 minutes. So now notice the difference here. What we have is that we have a sample size now. We have this n equals 10. This clues us in to let us know, I'm dealing with a sampling distribution. I'm no longer dealing with one sample, but multiple samples. And so what would happen if I took lots and lots of samples of size 10, so not 10 samples, but a lot of samples of 10 interruptions each. I keep saying interruptions, I'm sorry. Eruptions each. What's that going to look like? Well, since our distribution is already approximately normal, then I know my sampling distribution will be normal as well. So again, I'm going to go on to a clean sheet so that we can draw this out and see how this is slightly different than, and of course we'll get a very different answer than what we did in part A. Okay, so I've started out with the same information that I had on the previous screen. I've got an n equals 10, that's my sample size. I have the mean and standard deviation, and then of course I'm still looking for what's the probability that now the sample mean. What's the probability of me taking a sample of 10 eruptions and getting a mean wait time of more than 97 minutes? So that's going to be very different. That means that when I add up all those eruption times, so let me go ahead and draw this. So this is, I always like to put the sample size over here. If I'm not dealing with just one, if I'm dealing with n equals 2 or more, I'm always like to mark that on my graph. That reminds me that it's a sampling distribution, and it also helps if anybody's looking at my work, whether, if you have a tutor, you're sending something to me that you've worked on, you're sending something to the Learning Center, tutors, or whatever, everyone realizes that what we're doing. So of course we have our mean of 84, and now, based on what we learned earlier in section 8.1, not the central limit theorem, but what we know about to be true about sampling distributions, is that the standard error will be 27 divided by the square root of 10. And as I said before, I usually just leave it just like that. And I'll show you when we type it in our calculator, we can type it in just like that. So there's no reason to go in and calculate that, find some decimal answer. We can leave it just like that as a fraction with that square root in the denominator. All right, so I'm specifically looking now, again, I'm still looking for greater than 97. And so even though my picture looks similar as far as where I'm drawing the line and where I'm shading, this is going to be much farther away because I'm not 27. I mean, I was still within one standard deviation before, because 84 plus 27 is much less than 97, because that's, 13 away? So, that's like half a standard deviation above the mean. Now, we're definitely more than one standard deviation away. So this is what I want to find, and let me pull up the calculator for that. All right, so here is our calculator. Notice that it's almost, oh, nope, that's not right. That's the wrong one, sorry. I think I picked A again. Let me delete that. Try again. Yes. For some reason it didn't stay in alphabetical order. It put B before A in my list, which is strange. Okay, there we go. That's all right. Mistakes happen, but we caught it pretty quick. Okay, so there's our calculator. Now, again, I still have the same drawing. The only thing that's different, like literally one thing that changes, is this square root of 10, which I make sure and put in my calculator. So my lower is still 97. Lower, remember, less then is the left hand. So the lower side is the left hand or left hand side. That's 97. My upper, I'm technically going to infinity, but any very large number will work. My mean is still 84, but my standard deviation of what I'm looking for, my curve that I'm looking for, is this standard error, which is 27 over the square root of 10. And I can just put in 27 divided by, to get the square root, you want to do second and then the x squared button. That's going to get your square root symbol for you. Now, when I actually calculate this, I get a much smaller number. I get, let's see, let me go back to my pen. There we go. I get 0.0639. So we went from almost 32%, 0.3151, to barely 6%, 0.0639. So this was a pretty drastic change for this calculation. All right, so part C of this example just wants us to do the same thing, but now we're going to look at a random sample of 30 time intervals. So now n equals 30. This changes the distribution that we want to work with. And so let's take a look at what this will look like when we draw it out. Stick it in the calculator and let's see how different our answer is. All right, so once again, we're dealing with something that was normal to start with. So our sampling distribution will also be normally distributed. So I can start off by drawing my normal curve. And again, this is why I like marking what my sample size is on each picture. It just helps me to know, okay, this is a new problem. I need to recalculate my standard error. Now it's going to be 27 divided by the square root of 30. So I know I've got to redo that. I've got to change that. My mean is still 84. And I'm still looking for a sample mean of 30 values. So this means we've basically taken a month, although that wouldn't be a random selection, but you know, we've taken a month's worth of data, randomly selected across, you know, several years maybe of data. And we just want to know what, one each day, maybe for the month. We just measured how long was it in between eruptions. And we got a mean for those 30 values that's greater than 97. So again, we have a mean eruption time of 84. For this to be greater than 97 means we've got a lot of really big numbers to move that up that far. All right, so again, we want to put this in our calculator. Let me pull up that image. I'm going to get the correct one this time. There we go. So again, literally, the only thing I really even had to go in and change this time was to change the 1 of the 10 to a 3 for 30. So this is what's different. Instead of dividing by, instead of just plugging in 27 for the standard deviation, and instead of dividing by the square root of 10 in the previous example where we had a sample of size 10, I'm now going to divide by the square root of 30, which is the sample of size 30. So when I put this in and actually calculate, let's see here, I end up getting quite a small number indeed. So I'm going to have, looks like 0.0042. It's 417, but it would round to 42. And so not even half of a percent. So remember, when we change this to a percentage, I would move that decimal twice, and that would be 0.42%. So not even half of a percent of the time would this normally happen. So this is very unusual for this to occur. And this is something that we'll come back to when we get into chapter 10 and we start talking about hypothesis testing. So this idea that I got this sample, I have this very small chance of that actually happening if indeed the mean wait time is 84 minutes. So what does that look like? What does that mean? How can I interpret that? Those will be things that we talk about when we get to chapter 10. For right now, though, we're still in chapter 8, so we're not going to worry about what's coming up, but just know that we will see this again. But instead, we want to know, what effect does increasing the sample size have on the probability? So we went from, basically, kind of want to think about it, we kind of went from a sample of just 1. Again, that's not really taking a sample, that's just observing one eruption wait time, or the time between 2 eruptions, I guess. Then we did take a sample of size 10, and then we took another sample of size 30, and we said, what are the chances of us having this certain event happen? It being a longer than 97 minutes, or a mean wait time that was more than 97 minutes on average. And what did we see? Well, let's take a look. I've summarized it for at least these two on the next slide. All right, so here, remember we said that when our sample size was 10, we had 0.0639, so a little more than a 6% chance of ending up with an average wait time, a mean wait time, that was greater than 97 minutes. And then we also just found out that if we took a sample of size 30, then our chances, our probability of having a mean wait time greater than 97 minutes was not even 0.5%. A very, very unusual, very small chance of that happening. And so what happens is that as our sample size increases, the area in the tails of the normal curve gets smaller. So we saw that. We saw, if I can kind of draw just a so if it was 6%, that'd probably be, that's a little more than, a little less than 2 standard deviations away, because remember, 2 standard deviations away, if I'm thinking about my empirical rule, puts 2.5% to the right and the rest to the left. So I'm going to say maybe right there. Not quite 2 standard deviations away. And we saw that that area, so it's same numbers, 84 for the mean, 97 for the x value, or the x bar value. We saw that that was 0.0639. If we were to try and draw somewhat to scale this same situation, but with n equals 30, and that normal curve isn't great, but it's good enough. I still have an 84, but now I've got this small area. And again, if we remember back to the values we did when we did the empirical rule, if we were 3 standard deviations away, that little bitty bit in the tail was 0.0015. So I'm closer to 3 standard deviations away when I do that one there. And of course that probably should end up being a lot closer. Let's see if I can make that look just a little better. Normally I would just do the undo, but I kind of had gotten too far to do that. So let me just redraw it. So there we go. Oh yeah, well, darn. Nope. That looks pretty good. And so we're saying 97 might be about right there. And this is 84. And that's our standard error. So this little area right here, 4, 2, is much smaller for the same values. We're still 13 minutes above the mean, but that probability, that area, that percentage, all those things mean the same thing. Those are different, and in this case smaller when our sample size gets bigger. So that's the key thing to remember with our with our sampling distributions. Okay, so this last question, part E, still dealing with the same setup as our previous problems. So assuming that we have a mean of 84 minutes and a standard deviation of 27 minutes, let's say that we take a sample of 30 time intervals and we find the mean, and that mean weight is indeed longer than 97 minutes. What are some of our possible conclusions? Well, there's a couple of things that we might conclude, and this is where we have to be really careful and find out, make sure that we have our design, experimental design set up correctly, that we've sampled correctly, and all of those things that we did back in chapter 1. We want to make sure that we've done all that correctly so that our information and our data is valid. And then we're going to step into this next part of the class where we're going to talk about inferential. What can we infer or assume based on what we found? So we found a sample of 30 time intervals between eruptions of this one geyser, and we found that the mean of those 30 in our sample has a weight that's longer than 97 minutes. So one conclusion that we could have is that the population mean is actually greater than what we expected or what we thought it was, 84. So perhaps the population mean truly is higher. We thought it was 84 for whatever reason. We have historical data to say as much, but we've taken a sample, we've got this new information. Here's one interpretation of that data. The other possibility, there is another chance. It doesn't have to mean that 84-minute mean, population mean, is wrong. Hopefully by now we know samples vary. That's just one thing that we've been talking about from the very beginning. Just because I roll a die 10 times, I could roll a die 10 more times, and I'm probably not going to get the exact same result. So, samples can vary. So this could just be that the population mean is 84, but this is just a rare sample. This sample is unusual, but not, it doesn't necessarily mean that the population mean was wrong. And that's where we've got to come in with our inferential statistics that we'll learn about as we continue for the rest of the semester. Which one of these do we want to try and conclude? All right, a few things to remember. First of all, whenever we're looking at these problems in section 8, the very first thing you want to double check is, do I have a sample? So remember, in part A of the example that I went through a few minutes ago, we weren't dealing with a sample at that time. If I don't have a sample, then it's just chapter 7, use a normal CDF and do it like we were doing before we even started this section. If I do have a sample, then I can apply what I've learned in Chapter 8. The next question we want to ask: is the population normal to start with? And again, yes or no. If it is, then our sample size can be anything. So I can have a sample of size 2 or 2 million. I don't know why I would ever have a sample of size 2 million, but I could. If not, then our sample size must be greater than or equal to 30. And again, that 30, it may not have to be exactly that big, but based on what our textbook says, if our shape of our population is either unknown or skewed, then we need at least a sample size of 30. So even if it's uniform and we don't necessarily have to have that big of a sample size, we're still just going to kind of let that be our guide for as far as we're concerned. So you can just remember the examples that you saw in the interactive assignment that, may be able to be less depending on how skewed the distribution is, or depending on if it's a different shape. All right, something else to remember. We've got to make sure to adjust the mean and standard deviation. I'm going to abbreviate that SD. Now, of course, the mean actually doesn't change, but our notation does. So we want to do the mean with that little subscript x bar. That's going to equal the mean of the population. And then our standard error is going to be the standard deviation divided by the square root of n. So we've got to make sure we make that change when we're dealing with a sample. And one more thing to note, /correct. I was just looking at the guided notebook, and I thought our textbook used n equals 30. It actually says that even for highly skewed populations of household incomes for a town, this is on page 198 of the Chapter 8 that I mailed you, or that you downloaded from Momentum, at the bottom. Notice that even for highly skewed populations of household incomes for a town, the distribution of sample means is approximately normal for n equals 25. So in order to use the central limit theorem, I'm going to use that abbreviation, we need n to be greater than or equal to 25. I mean, honestly, you can still use n is greater than or equal to 30. I really think that as long as you're in that range, you're gonna be fine. So, just trying to look real quick and see. Yeah, they've got a sample of 35 in the last example. So, we'll say that according to our textbook. Okay. All right, so that should take care of section 8.1.